we are taking something from gamma, so we are having advantages of gamma code, as well as we are actually dealing with representing it in the MSB. So you are having it. So it can be considered as an advanced enhancement over gamma code. So the thing is same, like number 3 I have taken. Again, say you can see 1 plus floor of something, that is again 1. 1 plus 1 is 2. But the gamma code for 2 is, for unary, it is 0, 1. But for gamma code, so what is the 2 value? You look into the table, what you have made, just made a note of it. So it is 0, 1, 0.
Yes, ma'am.
So it is 0, 1, 0. So now what we do is, you take binary representation of 3, that is 1, 1, and you subtract 1 MSB. So you will get only 1. So the Elias gamma code for 3 is 0, 1, 0, 1. So earlier it was 3 bits, but now it is 4 bits. So binary representation is 2 bits. Elias gamma code is 3 bits, and Elias delta code. Sorry, here I have mentioned it as Elias gamma code. It is not gamma, it is delta. Okay. So Elias delta code is 4 bits. When you take small numbers, you usually fill it in that way. But when we take bigger numbers, like in hundreds or 200s, obviously you could see there is much advantageous. Okay, so now I want you to work similar fashion. You have to find the Elias delta code for the number 10. Okay, so you take x as 10 and quickly you look into the table what you have made a note of it, and just you can quickly tell me. So earlier you have already worked this 1 plus floor of log x base 2, that is log 10 base 2, you have already done it. Okay, so you have taken the value as 4. Am I correct? So it's 1 plus 3, that is 4. But in gamma code, you have taken unary value of 4, but now you have to take gamma code of 4. What is a gamma code of 4 from your table? So gamma code of 4 you have to copy from here. So how many bits it's taking? Okay, good. I'm getting answers in the chat. Okay. So it is 0, 0, 1, 0, 0. And you have to again take the MSB. So sorry, you take binary representation and remove MSB, as earlier Dheeraj was mentioning. So we have seen it as 1, 0, 1, 0. When you remove 1, you will get 0, 1, 0. So you will have 0, 0, 1, 0, 0, 0, 1, 0. So am I going too fast? I hope you people have done it already. I'm projecting it. The answer. So somebody is still coming to the class. Okay. So is it clear? Yes, good. Okay. So I think everybody will be able to follow this. So my objective for today's class is, if you are working along with me now, I don't want you to waste time again reading the textbook before your exam. Okay, you will not forget once you practice it. If you are working along with me now, I don't want you to waste time again reading the textbook before your exam. Okay, so now you have for number 10. You will not forget once you practice. Quickly tell me for number 8. Working along with me now, I don't want you to waste time again reading the textbook before your exam. Okay, so now you have for number 10. You will not forget once you practice. Quickly tell me for number 8. Kishore Reddy, 514. Can you give me the Elias delta code for number 8?
I'm doing it.
You are doing still?
Yes, ma'am.
Okay. Oh, what is the first component? You can work along with me. What is the first component? Log 8 base 2, right?
Yes, ma'am.
So what is log 8 base 2?
A floor of 3 point something, ma'am.
You will not get 3 point something. You'll get exactly 3. Log 8 base 2. 8 is 2 cube, right?
Yes, ma'am.
That's what I have given you in the table. Have you not made a note of it? So you get exactly 3. So there
Yes,
is no
ma'am.
need of working floor. So now
Yes,
what
ma'am.
happens? 1 plus 3 will be 4. So the gamma value will be same. So for 8, what is the decimal binary representation? Decimal 8
One-
binary representation. 1
1
followed by
0
3
0.
zeros. 1
Yes,
followed by 3 zeros. Remove the 1 most significant bit.
3 zeros.
So
0 0 0.
yes. So what is your final code? Tell me.
0 0 1 0 0 and then again 0 0 0.
000. That's all. Okay. So this is about Elias delta code. When I go for gamma code, in place first 5 digits, you will have only 4 digits because you will have unary. So 0001 triple zeros. But in delta code, you'll have 001 triple zeros, again 2 zeros, or 001 00 triple zero. Okay, so usually in exam you may expect to differentiate between a gamma code and delta code. Okay, so then what I expect my students to do is, so you just mention that when I ask you to when they ask you to make a comparison, you tell both of them have 2 components and both of them use binary representation, both of them use the representation, the unary representation or gamma representation. Okay, so good. People are responding over chat. Okay, this is about Elias delta code. And one more thing, what I want you people to make a note is, like now you already have the table, right? You have made a note of a gamma code. Just you add one more column and you try to make a note of Elias delta code. Sorry, this is delta code. Okay, I'll just make a change. Okay, so you quickly make a note of this. The same table, you add Elias delta code. And after I'll give you 1 minute, you make a quickly note of it. Then we will see more complex coding, Golem coding. Okay. Mukul? Mukul,
Yes,
at least you respond. Have you completed noting down? Nitish is joining now. So somebody is responding over chat. Why? Is it difficult to talk? Are you in a constrained environment?
Noted, ma'am.
Noted it. Okay. Can we move to the Golem code? Okay, so let me just take, instead of moving to Golem code, okay, so let us work on the 290, like in the inverted index, like I have taken the value as 290, right? Okay. So for 290, unary representation will be quite complex. Like you will have 289 zeros followed by 1. Is it clear? It's very lengthy, right? So how many bytes it takes? 290 is the integer. The x value, I want you to take it as 290. Note down x is equal to 290. So for unary coding, so how many bytes it require? Tell me quickly.
$290, ma'am.
No, not bits. I'm asking bytes.
Okay. Sorry, sir.
Because memory, we always do byte addressing, right? So I just want to give you that information. Nobody?
37 bytes.
Nobody learned abacus?
37, ma'am.
Yes, 37. Who is that? Muskan gave 37. Good.
Roshan.
Sandeep also gave. Who is that? I could not see you.
Roshan. Surya.
Okay, very good. Meena has given us 290 bits. Okay, 37. Nikhila also has given. Very good. So now if you see, if I go with a normal integer representation, you usually use only 4 bytes for 290. But when I'm going for unary, I'm using 37 bytes. It may look very complex. Okay, but that is preferred when I'm having a small log gaps. Like if I'm having 1, if I'm having 2. So I'm not using 4 bytes. I'm using only 2 bits, 3 bits, 4 bits, and the decoding will also be easy. Are you getting the comparison? So now let us work on for 290. Now I want alias gamma coding. And I'll ask randomly. For 87, Craig is not available. Is Sai Pavan available? Sorry, not Sai Pavan.
Yes,
Pavan.
ma'am.
So Pavan,
Yes, ma'am.
just now raised the hand, right? Pavan, Pavan, who is that? Reddy or?
Found ready, ma'am.
Pavan Reddy. Okay. Purnachand is coming now. So he is. Okay. So Pavan, can you tell me what is alias gamma code for 2x value 290?
I'm doing, ma'am.
You're
Log
doing.
value of 290 is
So
around 9,
now
ma'am.
you will come to know why delta coding has come into picture. Okay.
Yes.
So in gamma code, what is it we have to do? You have to take unary representation of a number. So what is that number?
Log 2
You
of
can work
290.
along with me, Pavan. You can just utter the things. So log
Fine.
290
2
base 2 plus 1,
plus
right?
1.
You
Yes.
have to take floor.
1 plus floor of 8.17. It's
So
9.
290 means
Yes.
you may have to take, so you can easily get this 256. So 256 and 512. You will get 290 between 256 and 512. Is it correct?
Yes, ma'am.
256 will be 2 to the power of
Uh,
8.
yes, ma'am. 2 to the power of 8.
So 2 to the power of 8. 512 is 2 to the power of 9.
9.
Okay.
Yes.
So 1 minute, you be online. So it's raining heavily here. I'll close the door. Did you get?
Yes, ma'am.
Okay.
Gamma.
So the log 290 floor when you take, you will get 8. Is it clear?
Yes, ma'am. Yes, ma'am. 1 plus 8, 9.
So 8 plus 1. So totally you will
9.
get the value as 9. So the
Yes, ma'am.
unary value of 9 Means you
One,
will have 8
one.
zeros.
Yes.
1.
8. Yes, ma'am.
Is it clear?
Yes,
Okay.
ma'am.
So somebody is giving me the answer. Okay, good. Again, 4 people. The regular 4 people who are active in talk also. So I want everybody's participation. That's actually the problem. So then the binary representation of 290.
Yes, ma'am. 1,
Sai
1,
Pavan, can you tell me what is the
Triple
binary
zero.
representation of 290?
1, 1,
How
1,
many
triple
bits
zero.
you have? Bits. I'm not asking bytes. As you know, we have taken it as 8 and 9, between 8 and 9. How many bits? It's 9 bits. Okay. So people actually are giving answers to everyone. Are you able to see that? So here if you see, a lot of people are giving the answers. So here if you see, you are having first 8 zeros followed by 1. Then you are removing the most significant bit. You are actually having, so 9 bits. So that is 1, 0, 0, 1, 0, 0, 1, 0. In one simple way, what I can tell you is 290 can be split as 256 plus 32 plus 2. Is it correct? So it's better you split it in that way. So 256 plus 32 plus 2. So that's why you'll have the most significant bit as 1. So you are cutting that 1. So you usually have it in this way. So majority number of times when we go for binary representations, we always have the most significant bit as 1. So just to avoid the redundancy, we are just clipping that 1. So here if you see, this is what is the answer. So now I want you to make a note. This is your alias gamma code for 290. Now I want you to give you the delta codes. So in delta code, what you should do? The last 8 bits, what you have now, will be same. The first bits will change. The first bits will change. So the first bits, like we have taken the unary representation of 9. Now I want you to look into the gamma table, what you have already taken. Okay, so I'll just move to the gamma. So right here. So now you see what is the gamma code for 9. Earlier we have taken unary code of 9, but now you will take gamma code of 9. So now you could observe here we have minimized few bits. How many bits you have minimized? How many bits you have minimized?
3 bits.
So you had 9 bits, but now you are having 7 bits. So 2 bits you have minimized because the binary representation will not change. Okay, the binary representation will not change. It is as it is. You are removing the most significant bit and you are copying it. But here you could observe you have minimized 2 bits because you have shifted from unary code to gamma code. So this is actually the advantage of alias delta coding. Is it clear? So again, I should not feel that I'm teaching only 5 or 6 members in the class. Pavan, is it clear? Is Vishwant Reddy available? Vishwant. So I think lateral entry 509. No, he is not available. Mahinder. Are you there, Mahinder? CH Mahinder.
Ma'am,
Mahendra. Okay, somebody is having a
Yes,
doubt.
ma'am.
Tell me.
Yeah, ma'am, like how many bits we need to discard?
Where?
Like you're telling that we have to discard this many bits.
Only
and
one.
that's it.
Most significant bit. I'm not giving plural there. Only
Yeah,
one bit.
That is in binary representation. ma'am.
Yes, it is in binary representation.
Okay, ma'am. Like I'm asking, like, do we need to discard any bits in the
No.
final answer?
No. You will not
Okay.
discard. That's what I'm telling you. First component, you look into the lookup table of gamma code, copy it. The second component, you write binary representation, remove the most significant bit and copy it as it is. And you're not trimming, you're not clipping, you're not changing the final answer. When you are computing the first component, you should be careful. And the second component is quite easy. Any person who knows binary representation, they can give you. Is it clear? Okay.
Yes, ma'am.
Who was that talking? I could not see your name.
Soumya, ma'am.
Soumya. Okay. Now let us move to a more complex coding. Why I'm telling you this is it is quite complex. So this also has two components, but it is not that simple. Like they're not taking just take log LB of that number and take floor of it, add one. They're not just doing it. They have little bit complicated. This will give you the less length. And they again have followed a statistical method. So that's why they're calling this as a parameterized coding. Okay. So I may take 2 or 3 more minutes, but I want to complete this column coding today. Variable byte coding also I'll complete today. And maybe tomorrow's class, I'll start latent semantic indexing. That's also quite important. So now I want you people to make a note of this. Golem coding also has 2 components for any number representation. Okay. The first component is, again, we are going back to unary representation. But here, when I'm going for unary representation, so here we are using a constant b. You take x and you divide with b, and whatever the quotient you get, you add 1 to it. Okay, that is in this way. You can see here. The first component is unary representation of the quotient plus 1. Then the second one is special binary representation of the remainder. So why we are calling it a special representation means, so again here people again started thinking, why should we take a binary representation? Like if I'm having a number 3, so why should I take 3 digits? Why should I represent as 0, 1, 1 when it's possible to store only 1, 1? 2 bits. So keeping that in mind, so they wanted to give a special binary representation. That is, the number of bits keeps on changing. So the special binary representation will be for the remainder. So you're having the constant b. When you divide the given x value with the b value, b will be fixed. If I'm following a system, I keep b value as 10. It is 10 always. For all numbers, it is 10. If for my convenience, I keep b as 3, I'll keep b as 3 for all the numbers. I want to keep b value as 5. Any number you can keep, the constant b value will be constant. When I'm dividing a given number, like the given x by b, I'm having 2 results. One is quotient and another one is remainder. Quotient is quite simple. Programming, you will get it. And you have to increment it by 1 and you will represent. The first component is quite simple. The second component is usually complex. So you know how you get remainder r. Okay, so you can tell x modulus b. That's simple. But when I am not using modulus operation, I should use it as x minus q into b. Okay, and when I tell q, it's always the integer. We are not taking the decimals. Is it clear? This part is quite simple. But after I go, that is b when I'm taking, I'm dividing with b. So obviously you might have studied it as equivalence classes concept. It will give you b different reminders. Like if you are starting with 0, you will have till b minus 1. So this is quite simple, right? Like if I take b as 3, how many reminders you get? 3 reminders. The values of the reminders will be 0, 1 and 2. Is it clear? This part is simple. This is simple mathematics, but later on we will be taking. So when I'm having 3, so again here I'm taking log 3 base 2. That is, I'm going to decide how many bits I'm using, how many bits, like I bits I'm using for some numbers and I plus 1 bits I'm using for other numbers. So that is the D value, how many I'm having, that is calculated with this equation. And I want you people to make a note. Okay. So you make a note. So this is quite simple, X by B. This is also simple reminder. But this is the D values should be coded with I bits. The remaining values, whatever you get, that is B minus D. Okay, B is total number, B minus D when you do. So those many values you are going to do with I plus 1 bits. Is it clear? I want you to make this a note. Now we will work out with an example. It will be very easy for you to understand. Now let us take B value as 3. Okay, for simplicity, I am taking number as X is equal to 1. Okay, so here when I take X is equal to 1, the base B, I am taking it as 3. I have to divide with 3. When I divide 1 by 3, the quotient is 0 and the remainder will be 1. That is 1 by 3, the remainder will be 1. This is quite simple. Now, what is the I? So I, as we have seen, we have to take floor of log 3 base 2. So you will get it as 1. Is it correct? So have you looking into the table what I have given? Till 4, you will get as 1. The I value will be 1. That means I'm having 3 reminders. Among the 3 reminders, 1 reminder I will have represented with 1 bit. The other 2 reminders I'm representing with 2 bits. Okay, this example, it may look simple. Okay, but I'm asking you to work with another digit. That time it may be difficult for you. Okay, so I want you people to make a note like this stepwise details. So now when I'm dividing any digit, any number with 3, you will have a base 3 will have 3 reminders. That is 0, 1, 2. So in 0, 1, 2, D is 1. That is 2 to the power of I plus 1. Okay, I is 1. I plus 1 is 2. So this is one thing. You people should be careful here. It is 2 to the power of 1 plus 1. It is 2 square. That is 4. 4 minus 3 will be, the B is 3. 4 minus 3, D will be 1. So here D is 1. So 0 is taking only 1 bit. Whereas 1 and 2, you are getting it 2 bits. So I bits, I plus 1 bits. So this is 1, 0 and 1, 1. So when you go with the code will be like this: unary representation of Q plus 1 and the remainder code for the remainder. So the remainder, like if you see here, the quotient is 0. 0 plus 1 is 1. What is the unary representation of 1? You look into your table because it is 1. Okay, so Mahinder responded me over chat. So if you see here, so the unary representation is 0 plus 1 is 1. So you will have it as only 1. And the remainder is, because I'm taking it as 1, the remainder is also 1. The remainder is coded, like 1 is coded with 2 bits, that is 1, 0. So the Golomb code for digit 1 with base 3 is 1, 1, 0. Okay, this is quite simple, right?
Ma'am, can you explain again the second part, the 1, 0?
Okay, I'll tell you. Actually, for this 1, 0, it is in this way. How I get that 1, 0? Okay, so I have to take 2 bits. Okay, so in order to have, how can I go to 2 bits? Like I cannot have 0, 1. Okay, 0, 1 is nothing but single digit 1. Why I can't have it as 0, 1? Why I should go with 1, 0? That usually will be decided using a coding tree. Okay, so the coding tree is a binary tree. So now if you see, you will have a node and it will have 2 children. The first children is annotated with 0 and the second children is annotated with 1. Okay, so but here I want 3 reminders. The first left child will have only 1 child. the right child, I can't have 1, I want 2. So what I do is I'll increase the depth of the right subtree. So the first one, I'm having it as representation for 0, whereas when I go for the right subtree, the annotated value for the right subtree is 1. So that 1 again will be followed by 0 and 1. So that node will again have a right subtree and right. Left will be 0 and right will be 1. Okay, so this is for 3 bits. So now I'll give you, just to give a more complex view, I have given you a B value for 5. Okay, now you just see, when I'm having the B value as 5, so that when I want B value as 3, it just looks in this way. Like you can clip it here. This is 0. Okay, you don't have these two. Are you able to follow the mouse cursor? This is 0. Okay, the leaf node, it becomes a leaf node 0. This leaf node becomes 1. This leaf node becomes 2. Okay, 0, 1 and 2. So 0 will be having the code as 0. 1 will be having, because I'm not having this. Okay, so this will be 1. So that is 1, 0 and 1, 1. Is it clear? If it is not clear, you just draw a tree. Okay, the node should have only 1 level in the left side, 2 levels, or the depth of 2 in the right side. Actually, for this, I planned to show you on the whiteboard. Is it clear? For B is equal to 3. So let me just check whether you can are you able to follow it, or shall I show you on whiteboard? So are you able to see the whiteboard?
Yes.
Yes, right? So it's for B is equal to 3, I'm drawing here. So I want 1 bit, but whereas the other side, I want 2 bits. So 2 bits means the depth should be 2. This is 0, 1. This is again 0, 1. The remainders, I'm representing it as 0, 1, 2. This is the remainder. The leaf node. Is it clear? Is it visible? Shall I make? So for 0, it is only this. For the remainder 0, it is 0. For the remainder 1, 1, 0. You will write it in this way. For remainder 2, it is 1, 1. I hope it's easy now. Is it okay? For B is equal to 3, I've given the tree to you. So is it clear to you now? Because this is actually quite complex in Golang.
Ma'am?
Tell me.
Ma'am, how did you know, like for B equal to 3, we will have only one value with 1 bit and 2 values with 2 bits?
That is what I have told you, D. Here, the computation D, right? I've asked you to make a note of this. D is equal to 2 to the power of I plus 1 minus B, where I is floor of log B base 2. Okay, so
Yeah, yes.
that's why I asked you to make a note of it. Now let us consider if B is 5. Take B as 5. Okay, forget about the number X. I'm not giving you the X now. I'm just asking you for B is equal to 5. So tell me how many reminders you will have. So I want the involvement of more people, please. Rahul, K. Rahul, 552. Are you there? So when B is equal to 5, how many reminders you will have? Normally when you divide with 5, you will have 5 reminders. Okay, the reminders will be starting from 0 to 4, right? The value, decimal values. 0, 1, 2, 3, 4. Am I correct? Now you have to find how many will be following I bits, how many will be following I plus 1 bits. So for that you have to take the value, D values. So D you take it as 2 to the power of I plus 1 minus B. What is I here? Log 5 base 2.
2.
How much you get? Floor when you take. Somebody is responding me over chat. Okay, Nikhila has given it as 2. Good. So I value will be 2, right? Because till you get decimal 8, you will have 2 point something, 2 point something. Once you reach 8, you get 3. Beyond 8 till 16, you get I value as 4. This is quite simple. Like for a decimal value 5, how many digits you want to represent? You want 3, minimum 3. But when you go to the floor of it, you will have 2. It's 2 point something, so you get as 2. So now when you go for D, it is 2 to the power of 2 plus 1 minus 5. B is 5. So 2 cube minus 5. So it is 8 minus 5. So what is the D value?
3.
3. Is the D value 3? So now what you have to do is, totally you have 5 decimal values. That is 0, 1, 2, 3, 4. Among them, 3 will be having 2 bits. The remaining 2 you will code it with 3 bits. Is it clear? That's what.
Yes, ma'am.
So first time when I have learned this, I have invested a lot of time. That's why I want my students not to waste time learning this. So I want to give you in a very simple way. So now here you can see. You want first 3 values. First 3 values. D is 3. So first 3 values you should have 2 bits. The remaining 2 values you should have 3 bits. So you start building the binary tree, the coding tree using a binary tree concept. So depth 2 bits means you should have depth as 2. So 0, 1, you will stop. Then you also want third one, but you can't extend here. You can't add it here. Okay, so always it should be, you should have a right skewed tree. You can't have a balanced tree. You will have a balanced tree only when the B is a perfect square or a perfect square of 2, power of 2, perfect power of 2. So here if you see, you are having it as 0, 1. 2 should also be using only 2 bits. Whereas for 3 and 4, you will have 3 bits. So that's why you will read it in this way. Is it clear? So now you have to represent the number 6. Okay. So now you take number 6 with base 5. What is our first step? Let me quickly take to you. I'm explaining you. I want you people to make a note of it. B is 5. So you take X as 6. So you want Q and you want R. So what is Q? 6 by 5. What is Q? What is 6 by 5?
1.
So quotient is 1. What about the remainder? Reminder, what is the reminder? You get quotient 1, remainder also 1?
Yeah.
Yes. So now what I want is quotient, I'm adding one more 1, like q plus 1. So I'm taking it as 2. So what is the unary representation of 2? Unary representation. Forget about Ilias gamma, Ilias delta. Go back to unary. So what is the unary representation of decimal 2? No answer. Vanilla, roll number 511. Okay, so people are giving me over chat. So why you're not having proper mics to talk? Okay, okay. So it is 0, 1. Now what is the code for remainder 1? Because it is 1, you can't take binary representation as one digit. You have to take how many digits we want according to this. So now you see this is 1. Okay, this is remainder 1 notation. This leaf is remainder 1. So what is the code for 1? You will read from the root. So 0, 1. So total representation for x is equal to 6, for b is equal to 5, you will have 0, 1, 0, 1. It is taking a nibble. It's taking 4 bits that we consider it as a nibble. For remainder codes, we will refer to this coding tree. Okay. Now you tell me, I want to represent 6, the same digit, x is equal to 6, but b is equal to 3. Now you tell me what is q? I've given on the board that 3 you have to refer now. For b is equal to 3. What is the remainder? 6 by 3. Quotient is?
2.
2. What is the remainder?
0.
0. So now again 2, you add it 1. The first component is q plus 1, that is 3. So the unary 3 will be 0, 0, 1. And the remainder, what you have seen. So in a base, when I take a base 3, so the 0 will have only one digit, that is 1 bit. So that I am having it as 0. So now when I'm taking base as 3, I'm having the notation, the value of the code as 0, 0, 1, 0. Whereas when I'm taking base as 5, the code is 0, 1, 0, 1. Is it clear? I hope it's clear. Can I move further? You want me to explain once again? So do you want me to explain it once again? So Minaz is telling me to continue further. Only one person is asking me to proceed further. Are you people hungry? Actually, I've also given for base is equal to 10. So if you're hungry and again at 2 o'clock you have a class. So tomorrow again I'll continue from this. Okay. Yes. Rahul, you're not talking when I'm asking you to talk, but you're hungry. You came late also. Okay, even I am hungry. My biological clock is set to exactly 1 p.m. Okay, so tomorrow class, I'll 2 o'clock you have my class Wednesday 2 to 3. So Charishma, I think she has informed you. So tomorrow I'll take few more examples, and I want all of you, like everybody should be ready to code about Gollum codes. Okay, so tomorrow let's take two more examples, and let us see again for 290, the same digit what we have seen with other codes. Okay. Okay, then give me 1 minute. I'll just make a note of your attendance. Charishma, have you taken the screenshots? If you have taken, I can wind up.
Yes, ma'am, already.
You have already taken?
Taken.
So very good, very good. Very responsible CR. Okay, so you share it with me. Okay, I'll end. Have your lunch. Don't sleep. 2 o'clock you have a class, I think, right?
Yes, ma'am.
And I want majority of you to talk in my class. I'll not get interest to just give one-way lecture. Okay? Okay. So let's meet tomorrow 2 o'clock. If you have any doubts,